Okay, let's see what we can do if we're looking at a group of order 12. So we can look at the two Sylow subgroups, which are the order 4 subgroups. We can look at the 3 Sylow subgroups, which are order 3 subgroups. The number of 2 Sylow subgroups is going to be congruent to 1 mod 2. And the number of 2 Sylow subgroups has to divide the index, which is 3. So that tells us that the number of 2 Sylow subgroups is going to be 1 or 3. The number of 3 Sylow subgroups is going to be congruent to 1 mod 3. And it's going to divide 4. And so that tells us that the 3 Sylow subgroups can be a number either 1 or 4. Oh no, okay, so we don't automatically, just looking at this, get that, that one of them has to be 1. Do we give up? No, we don't give up. We have to go on. So 3 is a small number. We have 3 of these 2 Sylow subgroups. We have, in other words, so let's focus on this case. You know, either the 2 Sylow subgroups the number are 1 or 3. If it's 1, we have a normal subgroup of order 4, and we consider that victory. Otherwise, we have 3 distinct Sylow subgroups, 3 distinct subgroups of order 4. But they're all conjugate. And G, therefore, acts on these 3 Sylow subgroups by permuting them by conjugation. So G acts on Sylow 2 of G by conjugation. The number of these is going to be 3 by assumption. Furthermore, they're a single orbit. We can think about so if P is one of them, Sylow 2 of G, I can say what is the stabilizer of that action? The stabilizer in G of P. Well, that's the normalizer in G of P. And what do I know? Well, by the orbit stabilizer theorem, the order of the group divided by the order of the stabilizer is the size of the orbit, which is all of them, which is 3. This thing is a 12. The normalizer, therefore, is 4. Which, of course, you know that P is contained inside the normalizer. So actually, this tells us that the normalizer is a Sylow 4 subgroup itself. Is P. Okay. And let's see, what else do we know? Well, because we're acting on this set with 3 things in it, we also get a map from G to the symmetric group of 3 elements, permutations of a 3-element set. And I can consider the kernel of that map. So if I call this phi, I can look at the kernel of phi. The kernel of phi stabilizes everything by definition. So this sits inside of the stabilizer of P, which is P. So this thing is a subgroup of G, and it either has, because it's a subgroup sitting inside of P, and it's a normal subgroup of G, the size of this thing is either 1 or 2 or 4, right? Okay, it's sitting inside of P, and it's normal, and P isn't normal by hypothesis. So therefore, it can't be the same. It's not going to be 4. On the other hand, it can't be 1 either, because the order of the group is 12. The order of the symmetric group of 3 elements is 6. And so the kernel has to have something in it, because 12 doesn't divide 6. It has to have at least 2 things in it. And it can't have 4 things in it, it can't have 1 thing, so it's therefore it has 2 things in it. Okay? So therefore, the size of the kernel is 2. And therefore, if n2 equals 3, there exists a normal subgroup of order 2. We can say a little bit more about that normal subgroup, in fact. It's actually kind of special. It's not just normal, but it's an order 2 subgroup that sits inside of all of the Sylow subgroups, right? The Sylow subgroups are conjugate to each other. We know that n is contained inside of one of the Sylow p subgroups because by Sylow 2, anything can be conjugated into a Sylow p subgroup. But if you conjugate both sides of this by g, using the fact that n is normal, you see that n is contained in the conjugate of the p Sylow subgroup. There are only 3 of these p Sylow subgroups, so that means that n is contained inside of p intersect p prime intersect p double prime, where these are the 3 distinct Sylow 2 subgroups in this case. In fact, it is that intersection. This is inequality. Because, well, I mean, what do you know? You know that these things are each order 4, right? N is order 2. You know n is contained inside there. If n, I mean, it's properly, how do I want to say this, right? I mean, the intersection of these things is non-empty because we know it contains n, and it's smaller than any of these things because they're not normal themselves, and so the only these things are all size 4. If it's smaller than any of them and non-trivial, it has to be order 2. The intersection has to therefore be n. That's the only possibility. So that means that n can be characterized as the intersection of all the Sylow 2 subgroups, but therefore it's preserved by any automorphism, and it's therefore characteristic. Okay? So in fact, a group of order 12 either has a Sylow 2 subgroup which is normal and therefore characteristic, or if it doesn't, the intersection of the Sylow 2 subgroups gives me a characteristic subgroup of order 2. So, so a group of order 12 always has a characteristic subgroup of either order 4 or order 2.